Hi, I'm excited to join you today and to provide an Earth observations perspective on agricultural monitoring in support of agricultural markets, sustainability, and food security decisions. As we're all well aware, we're only getting further and further away from the SDG goal of zero hunger, and food security remains one of the most critical challenges of our times, especially under a warming climate. Therefore, innovation is needed in developing robust and scalable measures to monitor the world's crops for addressing this global challenge. Recent major advances in satellite technologies, cloud compute, AI, GPS, and other digital technologies are enabling us to do this and are transforming the agricultural sector. These are enabling cost-effective monitoring of nearly every field across the globe on a near-daily basis and to enable us to track changes over the past several decades. And so here I'm showing a list of some of the main areas where remote sensing can make a significant contribution, and I'll give some examples of a few of these areas that we're working on under the NASA Harvest program. So NASA Harvest is NASA's Global Food Security and Agriculture program. It was launched in 2017, and it sits within the Applied Sciences program in the Earth Science Division. Under NASA Harvest, our mission is to enable and advance the adoption of satellite data to benefit food security, agriculture, and human and environmental resilience, and helping to bridge gaps between scientific findings and practical applications. So to accomplish our mission, we are organized around several different key focus areas that are listed here, and we have over 35 different active projects, which are all stakeholder-driven. And being end-user stakeholder-driven is really at the core of our work and ultimately is helpful in making an impact. So to enable nearly all of our activities, we have to have information on where crops are growing, when, which crop types, and what their productivity is. So when we pair ground data and machine learning models with satellite data and models can provide us with such information at a global all the way down to the field scale on where and when crops are growing and how those are changing through times in response to weather, markets, and policies. So here, looking at a global cropland extent of over 20 years, over the past 20 years, we can look at different patterns of change and see how croplands are expanding in many parts of the world, often at the expense of natural vegetation, which of course has major implications for the sustainability goals. So moving beyond cropland to mapping specific crop types, one would think that we know well where the main commodity crops are growing around the world. And while we have made great progress in mapping these crop types globally, there's still a lot of uncertainty, particularly for smallholder agricultural systems, where cropping systems can be very complex and hard to map. So to address these challenges, our machine learning team has been working extensively on innovating on methods to learn from sparse and heterogeneous labels for croplands and crop type mapping. And these help us to provide field-level information for different seasons depicting which crops are growing and where. And this kind of information is critical, for example, for informing crop area estimates, agricultural insurance, as well as to feed into different yield forecasting models. So in fact, another large area of focus for us is in applying different models to support improved crop yield forecasting and estimation at the field to global scales. And yield forecasts are critical for supporting market transparency, early warning of impending shortfalls, or for mobilizing humanitarian assistance and for supporting management decisions and efforts to target productivity-enhancing interventions. So ultimately, our goal is to translate these kinds of data products into actionable information in support of agriculture and food security decisions. And for this to be impactful over the long run, applications have to be co-developed and driven by stakeholders. And it's critical to consider from the start the capacity needs, the long-term sustainability of the application, and the needed ground data. Taking these tools, we can start to apply them to inform decisions and reduce uncertainty in crop estimates throughout the growing season. So this is a major initiative under the G20 GeoGLAM initiative called the Crop Monitor. It was developed in response to a request by the Agricultural Market Information System and the early warning communities to provide consensus-driven crop condition assessments that are easily understood by the policy communities. It brings together over 40 national and international organizations to provide operational monthly global assessments of major commodities and food security crops, and these are published on a monthly basis in 2 separate bulletins. So recognizing the value of the crop monitors, we've been working with regional and national entities to adopt and build on the crop monitor system to develop their own monitoring systems driven by their own national needs. This is another recent example of a partnership between FAO, the Ministry of Agriculture in Malawi, and NASA Harvest to advance yield forecasting and in-season crop condition monitoring in Malawi in support of the government using satellite data. Tools developed under this project were used in April of 2023 to assess the impact of Cyclone Freddy on agriculture and food security in southern Malawi, where they estimated crop loss in 73% of the impacted surveyed areas. So one of the newer initiatives that we've launched is focused on rapid agricultural assessments. The objective of this initiative is to establish a high-impact innovative framework that can provide timely, accurate, and actionable agricultural assessments to address critical information gaps in the face of increasing frequency and severity of extreme weather, in the face of conflict and war, or due to market uncertainty and other unforeseen events and disasters that can impact food production, trade, access, and ultimately food security. So under this initiative, we've been supporting the Ukrainian Ministry of Agriculture in their assessment of the impact of the war on their agricultural production. As you're all very well aware, Ukraine is a critical global breadbasket that prior to the war was responsible for approximately 10% of global wheat exports, close to 50% of sunflower oil exports, and provided approximately 40% of wheat food aid sourced by the World Food Programme. So following the start of the war, as we've had a long-standing partnership with several entities in Ukraine, we started working closely with the Ministry of Agrarian Policy and Food of Ukraine to assess how much of Ukrainian croplands were under Russian occupation and to help them monitor in particular over the occupied territories the impact of the war. So in April of 2022, we produced an in-season map of winter crops, those are largely wheat, versus potential spring-planted crops. And we found that about 23% of the total croplands and about 29% of winter crops were under Russian occupation. We've done the same analysis this year, and I'll show those results later on. So comparing our planted area estimates of winter crops for the 2022 season to the official statistics that were released prior to the war, as winter crops and largely that are winter wheat were planted in the fall prior to the start of the war. So we could build in our confidence in these assessments and being able to specifically monitor what was happening in the occupied territories. And here I'm showing a comparison of our planted area estimates versus the official estimates at the oblast level. So we were then asked to resolve two major uncertainties. First, how much of the spring and summer crops would be planted, given that there was a lot of speculation that 30% or more wouldn't be planted because of the war? And second, how much of the winter crops would be left unharvested? Again, the assumption here was anywhere from 30 to 50% would not be harvested. So we used a variety of different satellite data, including Sentinel-1, Sentinel-2, and Planet data to monitor first the planting progress and then the harvest. And actually what we found was that the majority of fields, including in the occupied territories, were indeed planted. And here the areas in green are winter crops, largely winter wheat that were planted before the war. And the red shows the progress of spring crops as they were being planted. And in fact, what we see is very little area was left unplanted. And this is looking at the Kherson Oblast. So as the season progressed, we could identify more and more different crop types. And this is a map of sunflower for 2022. And one thing to note is that we see a visible line across or just around the front line where sunflower was not planted, that area that has no blue dots, if you will, around it, where everything that's blue were where we detected planting of sunflower. We then automatically also delineated all the field boundaries within the growing season across Ukraine, and we use this for different parts of our analysis that I'll show. So ultimately, we classified winter cereals, winter rapeseed, sunflower, and then other summer planted crops. And we found that Russia was occupying a significant area of several of the major commodity crops, as you can see here. Using the crop type maps as an input, we ran different yield models at the field scale and all the way up at the oblast to national scales to estimate yields, particularly in the occupied territories where yield data wasn't available. And ultimately, we used the ministry's yield data for Ukrainian held territories and used our yield estimates over the occupied territories. And I'll share these results as well also for this current year. So it wasn't enough to estimate yield and planted area, if ultimately to get at production, given that there was a large concern again about how much of the wheat would not be harvested. So we also needed to be able to estimate the proportion of area that would not be harvested. And so to illustrate the signal we were looking for, I'm showing here a time series of a wheat field going from early vegetative stages after dormancy all the way through as it is very bright green, the max biomass, and then as it was drying out and senescing down to harvest. And what you see, where you see the bright yellow signal, that's the harvest signal, which corresponds to the crop residue that's left after harvest. And you can see finally the field was entirely harvested and then plowed over. So this was a signal that we used to progressively classify harvested versus non-harvested fields as the harvest season progressed. And what we found was that, by and large, the large majority of fields were indeed harvested, including in the occupied territories, with only 12% of fields in the Russian-held areas that were not harvested. And as we were going through the validation of our results, we also found several examples of fields that, despite shelling, were still being harvested. And that's that field here that you can see marked with an X. So we could then finally derive our total production of wheat for 2022, and we could also provide those estimates with Ukrainian-held versus Russian-held territories. And what we found was that much more had been harvested than had been expected. And ultimately, the production for Ukraine was much higher than most estimates were showing, with 5.8 million tons of the harvested wheat harvested in occupied territories, which translates to around 22% of Ukraine's production of the 22 season. And this, of course, had major implications for Ukraine as well as for markets. And so, of course, what we don't know, or what we couldn't monitor from our side, is what was happening to that 22% of wheat that was harvested in the occupied territories, where it ended up, who reaped the economic benefits. But what we could see is that indeed it had largely been harvested. And so we've done the same for this year, and looking at this year, we've run through very much the same steps and found that the total cropland under occupation is down to about 20%, with winter cereals down to about 23%. And these are all significant, but of course are reduced relative to last year, both due to the reduced area planted and also due to gains in the Ukrainian side relative to July of 2022. And so these are our estimates for the 2023 season. We just released earlier this month. Again, we see actually a total production that we're estimating right now, similar to last year's production, but with lower planted areas, but higher yields than were last year. And again, we broke out those numbers by Ukrainian-controlled versus Russian-controlled territories. So another area we've been looking at is doing damage assessments to monitoring the agricultural area, in particular around the front line, as we know that area has been extremely heavily shelled. And so what we can do is map the individual craters on fields. And of course, this also becomes an important indicator of where there might be unexploded ordnance and is very critical for demining operations. So far, we've mapped around 2.5 million artillery and rocket impacts across the front line, and we've mapped around 33,000 square kilometers. And so when we overlay these areas of fields with craters with our field boundaries that I showed earlier, we can start to look at heat maps or concentrations of craters within agricultural fields across the front line. And here we can see areas or fields that have upwards of 3,000 craters in just one field. Even more recently, one of the things we were asked to do was to assess the damage of the dam collapse and looking at particular agricultural areas. And so one of the main things that we looked at were actually the irrigation canals. This is the reservoir is a major water source for irrigation in this area in southern Ukraine. And so we first were monitoring the inlets to 4 of the major irrigation canals. And what we found, and here I'm just showing an animation of one of these, of the North Crimean Canal inlet, but these are all now disconnected from the reservoir. And this, of course, will have major implications for irrigated areas in this region. So we've also mapped the flooding extent based on 3-meter planet imagery. And so here you can see in dark blue where the initial water was flowing, and then the lighter blue is the areas that have been flooded. We overlaid on top of that villages or settlements, and you can see here in yellow, those are different settlements along the floodplain. And the areas that are in bright green are the parts of those settlements or cities that have been flooded. And so here we can zoom in, for example, to southern Kherson, and you can see the entire southern part and the port are completely underwater, or were completely underwater. Now the waters are in fact receding. And so we can also monitor the receding waters. The area here in dark blue is the area that has actually dried up as of June 9th, and that, of course, has been progressing. And so finally, we could also look at how much area of croplands were flooded, and we found that it was actually a very small amount. It was around 5 square kilometers of flooded area of croplands. But again, the major impact on croplands is not the flooded areas, but rather the lack of irrigation. And so ultimately, these data have been used by a variety of different governments and organizations, but most importantly, have been used by the Ukrainian government to inform their market decisions and agricultural policies. And so I also would like to acknowledge the team that has been working on this round the clock, I would say, for the past more than a year now, both on the NASA Harvest side as well as our partners on the Ukrainian side. And so to conclude, advances in remote sensing and AI and machine learning and cloud computing and digital data GPS technologies are really revolutionizing the agricultural sector. And with the ongoing, or I guess over pandemic at this point, the increasing extreme weather events really highlight the need for transparent, actionable information from space to inform food production, agricultural markets, trade, and disaster response measures. And it's really critical to see and to have international cooperation, such as within different organizations, different countries, and different sectors, to ultimately help to realize the full potential that Earth observations offer to inform key policies and decisions at the farm to global scales. With that, thank you.